All right, welcome to Unit 8 on acids and bases. We're looking at topics 8 and 10, properties of buffers and buffer capacity. So we will be determining what a buffer solution is, as well as its pH, and what the properties of buffer solutions are, as well as what buffer capacity is. So what are buffer solutions? Buffer solutions contain large concentrations of both members of a conjugate acid-base pair, and they need to be equal molar solutions to be the best buffer. So an example, the acid in the pair can react with the base that's added to the solution, while the base in the solution can react with the acid added to it. So if you have a conjugate acid-base pair, say we have a weak acid and its conjugate base, and we have equal molar solutions of it poured together, you can add strong acid and the conjugate base will react and the pH won't change that much. Or if you added a bunch of strong base, the weak acid would react with it and the pH wouldn't change that much. So these solutions are able to stabilize the pH and resist drastic pH changes. Okay. So what are the components of a buffer solution? So you can have a weak acid and its conjugate base. So for instance, acetic acid and an acetate ion. Those two things would form in equal molar solutions, a really nice buffer. Excuse me. A weak base, or we could have a weak base and its conjugate acid. So ammonia is a weak base. Its conjugate acid would be ammonium ion. So if we mix those, we could get that buffer solution. So we want to look for a weak acid and its conjugate base, or a weak base and its conjugate acid. A lot of times with the weak acid, it will be some sort of ic acid and an ate ion. So acetic acid and acetate ion, or chloric acid and chlorate ion, that sort of thing. So how do we find the pH of a buffer solution? This is actually something we've done before in another capacity, but we're just going to look at it from a different angle. So if this is the equilibrium expression for a weak acid, shown here, a buffer solution is made where the concentration of your weak acid on the bottom is equal to the concentration of the conjugate base, A minus, on the top. So if those two are the same, they would cancel out. And so that means that our equilibrium constant would equal our hydronium or hydrogen ion concentration. So this makes it pretty easy to find the pH. If the negative log is taken for both sides of the reaction or of the equation, then the pH equals the pKa. So if we negative log both sides, negative log of the right side would give us our pH, negative log of the left side would give us our pKa. So pH equals pKa. And we saw this at the half equivalence point on our titrations in our last couple of videos. So we've been using a rearranged version of this equation to solve for our hydronium ion. So we've seen this equation solving for the hydronium or hydrogen ion. And so we can use the same equation. The same idea applies. Acid is equal to the conjugate base concentrations. This all turns into a big 1. We've seen that before when these are equal concentrations. That's at that half equivalence point. So pH, if we take the P for both sides, pH equals pKa. So that's how we can find the pH of a buffer solution when we have equal molar acid and conjugate base. So what are some of the properties of a buffer solution? A buffer solution can maintain the pH at a fairly constant level with it either a strong acid or strong base being added to the solution. So if we had, sorry, let me get my words together. So when a small amount of strong acid is added to our buffer solution, then the pH will decrease slightly. So if we add acid, we're going to bring down that pH to being more acidic, but it's only going to happen slightly. When a small amount of base is added, then to our buffer solution, the pH will increase slightly, become a little more basic. But as long as that ratio of acid to conjugate base or base to conjugate acid is fairly constant, the pH of the buffer solution will not change very much. So we can see if the ratio is 1 to 1, those cancel, our pH equals our pKa. Now, if I add an acid or base, in this case, we're increasing the amount of acid, so it reacts with some of the base, a little more acid here. So if that occurs, then we change this ratio from being 1 to 1, but it's still really close to each other. The values are very close, so it's not going to affect our pH that much. Similarly here and here. So when we maintain that really close ratio of acid to base, then we're going to maintain our pH. So adding strong acid will decrease our pH, adding strong base will increase our pH, but only slightly. So we can see an application of the same principle in a weak, strong titration curve. So in this first one, we have a weak acid and a strong base. We can tell first that the equivalence point is at a pH above 7. So that's telling us that we've got that strong base, we're more basic, and we've got that weak acid. Excuse me. We can see that our equivalence point would be at 50, so our half equivalence point would be at 25. So letter C is where we create that perfect buffer. Okay, we've got that 1-to-1 ratio of acid to conjugate base. Now, if we were to have a little bit more acid, then our pH would decrease. We would be around letter B. And if we had a little more base, we'd be around letter D. And have a little higher pH. In this region, though, we call it the buffer region. So we tend to see that in titration curves. When we start out our titration, we're going to have a little bit more drastic increase or decrease, depending on which type of titration we're doing. And then we're going to see it just gradually change pH, and that's our buffer region. We can see the same thing illustrated with a weak base and a strong acid. We're starting out in the basic region. So we're starting with base in our container, and then we're adding the acid. Again, our equivalence point is at 50 milliliters, so our half equivalence point would be 25. So C would be our half equivalence point, make that 1-to-1 ratio with the buffer. And then again, if we had a little more base, we'd be a little higher pH. A little more acid, be a little lower pH, and that would be our buffer region on the graph. Let's take a look at an example of how to calculate our pH of our buffer solution. So buffer solution is prepared by combining 500 milliliters of 2 molar acetic acid with 500 milliliters of 2 molar sodium acetate. So we've got that ic acid and that 8 ion. So the Ka for acetic acid is 1.8 times 10 to the negative 5. So we want to find our pH of that buffer solution. So we're going to start with this equation we've been using in the unit. Hydrogen ion equals the Ka of your acid over base. So weak acid over conjugate base. So we can plug in our values for this. We've got our Ka value given. And then for our concentrations on the top and the bottom, we can take our molarity, so 2 molar, and multiply it by our volume in liters, so 0.5 liters. 2 times 0.5 would give us 1. And that is the same for both the acid and its conjugate base. And if we did add these together, they would both be divided by 1 liter. So 1 mole over 1 liter is 1 molar. But you really don't have to worry about the liters. You can plug moles into these. Excuse me. So once we have that shows us that term 1 over 1 is just 1. So our hydrogen ion concentration is really 1.8 times 10 to the negative 5. So we can negative log both sides. If we negative log the left side, we get our pH. On the right side, we get negative log of the Ka, gives us our pKa, which is 4.74. So that is our prepared buffer solution. Now, part B says to write the net ionic equation for the reaction that occurs when HNO3 or any strong acid is added to this buffer solution. So when you have a strong acid, something to remember that The ion here is your spectator. That's not really what's reacting. It's that hydrogen ion that's really reacting. So if we were to do this calculation, or excuse me, do this reaction, we'd have our acid there from our strong acid reacting with the conjugate base, so that conjugate base of the acid from our buffer solution. When those react, we're going to get that more of that acid, that weak acid formed. So when you add acid, it's reacting with the conjugate base to form more of the weak acid. Now part C asks when a small amount of HNO3 or any strong acid is added to the buffer solution, the concentration of the weak acid will increase. We can see that that's being formed in the reaction, and the conjugate base will decrease, right? We're using up some of that in the reaction by it reacting with our strong acid, so it's going to decrease. Continuing on, this is like an FRQ type question. So it says, suppose that 4 milliliters of 10 molar HNO3 is added to 1 liter of this buffer solution. Calculate the pH of the buffer solution after HNO3 is added. Assume the final volume of the solution remains constant at 1 liter. So we're basically saying that those 4 milliliters, we're adding them in, but we're not going to worry about the change in volume. Okay. So we're still going to use that same equation, Ka of the acid over base. We've got our Ka value, and this is where we're going to do a little adjusting. We had a 1 mole to 1 mole ratio, but we're adding more acid. So on the top is our acid. So 4 milliliters times 10 molar. If we change our milliliters to liters and then multiply by our molarity, we get 0.04. So we're adding more of that to the acid. And when we add that acid in, it's reacting with that conjugate base. So we're going to lose some of our conjugate base here, which is why we're subtracting. Adding on the top, subtracting on the bottom. If we simplify that, we get 1.04 and 0.96 on the bottom. That's a really close to 1 ratio, right? It's not very drastic, even though we've added a really strong amount of acid. We've added a 10 molar solution. We've only added 4 milliliters of it, but it's just altering that ratio a little bit. So if we do the math, we get 2 times 10 to the negative 5 as our answer for this. Now, if we want to know the pH, we're going to negative log both sides. So pH is going to equal the negative log of that value, which gives us 4.70. Now on the previous slide, our buffer solution by itself had a pH of 4.74. So we can see that adding some strong acid, although it's a very concentrated solution, does not alter our pH that much. Again, because we've already got some of that conjugate acid, or that acid base pair in there, it's going to kind of counterbalance each other. So let's see what happens when you add some base. So same kind of scenario. Suppose 4 milliliters of 10 molar KOH, so strong base, is added to our buffer solution. Calculate our pH. So same setup, but this time to our 1 mole solutions, we are going to add to the base. So we're going to add on the bottom because we're adding strong base. And it's going to react with some of the acid, the weak acid. So we're going to subtract some of the weak acid. So when we do that and simplify, we get 0.96 over 1.04. Again, that ratio is very close to 1. So we shouldn't get a drastic change here. We can see that's only altering it a little bit in terms of our value here. We negative log both sides and get our pH. So pH equals the negative log of 1.7 times 10 to the negative 5. We get 4.77. So again, our buffer solution by itself is 4.74. We add acid, we drop it down a little bit to 4.7. We add base, we raise it a little bit to 4.77. But we're not getting a drastic change in the pH. It's a slight change. So that reflects that buffer region on our titration curve, where it's almost flatlining, but not quite. So to prepare a buffer solution, if we want to make one, we want one of two options. We want to combine equimolar to equal moles solutions of weak acid and its conjugate. So just like we saw on the previous slide, a weak acid like acetic acid, and then the acetate ion from a salt. So we want equal molar of that. But the other option is we can think about a titration and think about making that half equivalence point. So we can combine a weak acid with half as much strong base. If this route is taken, then it's the same as the half equivalence point in a titration. So basically you're titrating half of your weak acid, and then you have half of it left over, and you've converted the other half into its conjugate base. So you get to the same endpoint, but it's a little bit different route. So let's take a look at these. Excuse me. The pKa of HNO2 is 3.4. Select all the following descriptions that would result in the formation of a buffer with a pH of 3.4. So our first one has that weak acid HNO2, and then has the same volume and molarity of KNO2. So KNO2 would split, you have potassium ion and then the NO2 ion. The NO2 minus ion would be the conjugate base of HNO2. So that would be a good candidate for making a buffer solution. The next one starts the same, 100 milliliters, 1 molar of HNO2. This time we're reacting the same volume and molarity of KOH. That's a strong base. If we wanted to go that route, we would need half as much strong base. Okay, so that one won't work. Okay. On the third one, we've got HNO2. We're combining it with HNO3. Those are a weak acid and a strong acid. That's not going to work ever. Okay, we don't have any conjugate happening there. All right, now we're upping our volume of our HNO2. So we've got 200 milliliters of 1 molar HNO2, and then 100 milliliters, so half as much of the 1 molar KNO2. Well, KNO2 is that conjugate base. We've got that NO2 in common there, but we don't have equal molar, so that one won't work. The next one, again, 200 milliliters of 1 molar of our weak acid. We've now got half as much, same 1 molar, but of a strong base. So we've got weak acid with a strong base, and we've got the half amount. So that's our half equivalence point. That is a good candidate for making a buffer. That's using that second option. And then our last one, again, has HNO2 and HNO3. Weak acid and strong acid, that's never going to work. All right, so those are some ways we can look at these, analyzing them. We either want that weak acid and equal amount of the conjugate base, or we want a weak acid and half the amount of a strong base. So we can also take a look at how to prepare a buffer solution when we're dealing with bases. So again, we want to combine equal molar solutions of weak base and its conjugate acid, or we can combine that weak base with half as much strong acid, and then with that route, we're at that half equivalence point. So pKa of NH4 plus is 9.26. So we could also flip this and say pKb of NH3 and get the pKb value. Select all the following descriptions that would result in the formation of a buffer with a pH of 9.26. So we've got a weak base, NH3, and then its conjugate acid, NH4 plus. We know that's the conjugate acid because it's giving us pKa, and the NH4 plus, that's the acid form. So if we combine a weak base with its conjugate acid, we'd want that 1-to-1 ratio, that equal molar ratio. So this one, we have equal milliliters, equal molarity, so we are good. That would give us a buffer solution. Here we can see we have that weak base, same amount, and we are mixing it with a strong acid, HNO3. Now that strong acid would not work with this unless they were that half equivalence point, so that one's not going to work. We've got here weak base with a strong base. So base and base are not going to work. We don't get our conjugate acid that we need. Okay, now we're doubling the amount, so the moles of our base. So if we want to have that buffer solution, if we're going to do that half value, then we need to have a strong acid. So here we've got weak base and the conjugate acid. but don't have that equal molar, so that wouldn't work. Here we have the weak base and a strong acid. That's going to give us that half equivalence point. That's going to be our buffer. And then last we have weak base and strong base. Never going to work. Can't have base and base. So just to summarize what we've seen, there are 4 possible combinations that should result in the formation of a buffer. So reminder, this is our weak acid and its conjugate, weak base and its conjugate when it takes hydrogen. So we can have the weak acid and its conjugate equal molar to form that buffer solution. Or we can have a weak acid and a strong base. Moles of our hydroxide are half the moles of the acid. So it's that half equivalence point, and it will react some of this weak acid into its conjugate form, half of it actually, and we get that buffer solution. Same thing for bases. We can have that weak base and its conjugate form in equal moles, or we can have the weak base and a strong acid at half the equivalence point, and we'll get our buffer solution. Okay. Now we're going to take a look at topic 8.10, which is called buffer capacity. It refers to the amount of acid or base that a buffer can react with without experiencing a significant change in pH. If the amount of acid or base that is added to a buffer exceeds the buffer capacity, then the buffer solution will experience a large change in pH. So there's like a range, right? We can add some acid and some strong base to our buffer solutions without changing their pH drastically, but there is a limit. So we can change, the buffer capacity by increasing the concentration of the buffer components while keeping their ratio the same. This keeps the pH of the buffer the same, but increases the capacity of the buffer to neutralize added acid or base. So we could have like 1 molar solutions that are combined to make our buffer, or we could have 2 molar solutions. Our 2 molar solutions are going to have higher buffer capacity. So let's look further at that. So let's take a look at buffer capacity in an example. So 2 different buffer solutions are prepared by combining solutions of acetic acid and sodium acetate. We're continuing that same chemical. As described in the table below, the Ka for the acetic acid is 1.8 times 10 to the negative 5. Now we can see for buffer number 1 that we are given 1 molar solution and 1 molar solution, and we're combining those in equal volumes. So our pH there would equal our pKa, which would be 4.74. We can see the same thing is true for buffer number 2. We're just using a lower molarity solution. So it would still have the same pH because it, again, equals the pKa, 4.74. So now let's see how they respond to changes in those pHs, to additions of acid or base. So again, that pH is 4.74, so we've got that as a reference. So a sample of 0.045 moles of strong acid, HNO3, is added to our 1 liter of buffer number 1. Assume the added volume is negligible, so we're going to ignore the fact that we've added a little bit of volume. Calculate the pH of the solution after HNO3 is added. So we're going to use our same equation, the Ka times our acid over our base. Now, for buffer number 1, we had 1 molar of each of them, the acid and the conjugate base. So we're going to start with 1 molar of each. Now we are adding extra strong acid, so we're going to add that 0.045 to the top. And when we add that, it's going to react with some of the conjugate base, so we're going to subtract from our conjugate base on the bottom. To simplify that, we would get 1.045 on the top and 0.955 on the bottom. Again, that ratio is still pretty close to 1, not very drastic there. So if we calculate it, we get 1.97 times 10 to the negative 5th. If we negative log both sides, we get pH, and that is going to give us 4.71. So we can see that adding a little bit of strong acid to our first buffer does not change its pH very much, only by 0.03. Now in part C, we've got that same amount of strong acid. Now it's added to a liter of buffer number 2. with all the same conditions. Now, buffer number 2 had a different molarity. It only had a molarity of 0.05. So we set up the same equation. We're adding acid. The acid's gonna react with some of our conjugate base, so we're gonna subtract from there. So if we simplify this, now we've got 0.095 divided by 0.005. That's a pretty different ratio there than what we've seen before. Not very close to 1. We can also see that the change here on the first one from our Ka to our hydrogen ion concentration was very slight, and here we've changed a whole exponent. So we're seeing a lot bigger change here. So what's our pH? We negative log that. Oops, sorry, that's supposed to be a -4. I did calculate it correctly though. This is the right answer. We get 3.47. So that is a definite change in our pH. We're dropping like almost 1.5, maybe 1.25, 1.25 pH levels by adding that acid. So we're adding the same amount of strong acid, but to a different amount of buffer, right? A different ratio set up for our buffer. So which buffer solution, 1 or 2, experienced a greater change in pH after the addition of HNO3? Number 2 experienced a greater change in pH. So which buffer solution has a greater buffer capacity? The one that doesn't change as much is the one that has the greater capacity to be a buffer, the better situation for being a buffer. So that's going to be number 1, right? All right, let's look at one more aspect of buffer capacity. This is our last slide. So when a buffer has more conjugate acid than base, it has a greater buffer capacity for the addition of added base than acid. So if I have a buffer and it has more conjugate acid than base. So say I've got a lot of my weak acid, right, and less of my conjugate base. Okay, we'll just draw them big and little to represent that. It would have the greater buffer capacity for addition of added base than acid, because if I add base to this solution, that strong base is going to react with my acid and shift that equilibrium. Okay, so since I have a lot of acid there, I'm able to accept a lot of base. Now we could have the opposite. If I had more conjugate base than acid, then we'd have a greater capacity for adding acid than base. So whichever one we have in greater concentration, it's going to be able to counter whatever we're adding to it. So if I have more base, it's going to be able to counter that added acid. If I have more acid, it's going to be able to counter that added base. So let's take an example, 0.75 molar HF, so that's my weak acid, and 1.25 molar KF, so that's my conjugate base, right? That F minus gives us that conjugate base. So they're mixed to create that buffer. So since we have more of the conjugate base, the buffer has a greater capacity for the addition of added acid because it contains that higher concentration of the conjugate base. Okay, it can counteract that acid. Where if we added more base to this, we don't have enough acid to react with it. Throws off that ratio too much. If we looked at number 2, or the second example, we got 1 molar HF and 0.67 molar KF. So again, we have a higher amount of the acid. So it has a greater buffer capacity for the addition of added base because it contains a higher concentration of the acid. So since we have more acid, we can react with the base. So that's how buffer capacity works. It can work both in looking at the total molarity, like we did on the last slide, the molarity of the acid and the base, having that same ratio, but increasing that ratio to a higher molarity or decreasing it. Higher molarity for our acid and conjugate base are going to give us higher buffer capacity. Lower molarity is going to give us our lower capacity and get a more drastic change in pH. Or if we don't have equal molar, those aren't ideal buffers, but we can use them. The one that's in higher concentration is able to accept more of the invader, basically, whatever we're adding, and keep that pH more stable. So if I have extra conjugate base, then I can add more acid. If I have extra conjugate or extra acid, I can add more base to the solution and not get that drastic change in pH. All right, so work on your practice. Whatever questions you have, let me know, and have a good one.